Okay, this is the video for Math 3, Unit 2, Objective 1. And for this objective here, we're going to be analyzing piecewise defined functions. So this is similar to our Objective 5 and 6 from last unit. So if you don't already, you should have a highlighter out or a colored pen or pencil. Okay, so just to go over some definitions. So the definitions we need to know, and they're kind of intuitive, which is nice, is that we have something that we need to know is increasing. So a function is increasing on an interval when the y values increase or as x increases. So essentially what that just means is as we go from left to right, our function is going uphill. So our function is going uphill, that would be considered increasing. And that is true regardless of where the arrow is. So I can draw an arrow that looks like that, and that is still increasing because as I move from left to right, we are going uphill. So it doesn't matter where the arrow is, as long as I'm going uphill from left to right, then that is considered increasing. So these are both increasing, even though I have an arrow here or an arrow here. And then decreasing. So a function is decreasing when the y values decrease as x increases. So decreasing, so again, that's kind of intuitive. So as we're going left to right, our function needs to be going downhill. So that would be something that looks like that. That would be considered decreasing. And even if I put the arrow on the other end, it is still considered decreasing. Okay, so it doesn't matter where the arrow is. It's what the line is doing. So as I'm going from left to right, I'm traveling downhill, so my function is decreasing. And then a constant is the y value stays the same. So when the y values stay the same. So that would be a horizontal line. So a horizontal line is considered a constant. Okay. Okay, relative maximum. So that is the point at which the function changes from increasing to decreasing. So from increasing to decreasing, that is a relative maximum. So if I'm increasing and then decreasing, right, that would be a relative maximum. So this point right here at the top, that would be considered a relative maximum. And it doesn't have to be like a parabola, it could be an absolute value graph. So essentially kind of like the vertex of a negative absolute value or negative parabola. So relative maximum when we go from increasing to decreasing. So then a relative minimum, the point at which the function changes from decreasing to increasing. So the reverse, right? So a minimum when we go from decreasing to increasing, then this point right here, that would be my relative minimum. Or decreasing to increasing, that would be my relative minimum. Okay? All right, so those are just kind of our basic definitions. Some of them are kind of intuitive, like increasing, decreasing, constant. Max, make sure you understand it's when it switches from increasing to decreasing, a relative minimum, decreasing to increasing, okay? All right, so let's go ahead and take a look at these examples. Let me zoom in just a little bit here. Okay, so answer the following questions about the piecewise defined function below. So this is a piecewise function. We have a negative parabola attached to a special case or constant graph. So state the open interval on which f is increasing. So for starters, when we see the word open interval, we need to know what that means. So open interval, open means we are always using parentheses. That's what open means. So even if it's a solid dot or a closed dot, we still are going to use parentheses. That's what the word open means. So open interval, we need to use parentheses. Interval, so remember what interval means. Interval means that we are going from x equals to x equals. So we're going from left to right. And we're using x values. So we're going from left to right and we're using x values. Okay, so we want to find where the function is increasing. So I'm looking to see where it's going uphill, so where it's going uphill. So if I look at this graph right here, so I'm always going to start from the farthest left. I'm ignoring the arrows. The arrows are not helpful for determining increasing, because some people will see this and they'll say, oh, we're going downhill because the arrow's pointed down. Okay, but we're going increasing. So I'm going to start here, and I'm looking to see, am I going upwards? And I am, right? As I head this way, I'm going upwards. So this section right here is increasing, right? So that section is increasing. And then once I get to the top, then I'm going to turn and start headed down, so that's no longer increasing, right? So this is now decreasing on this section. So this section is increasing. INC increasing, and then after that, now I'm going downhill, so that section is decreasing. And then now when I turn, now I'm going constant. So this is not increasing or decreasing, this section here is constant. So we're going uphill, then we're going downhill, and then we're going constant. So up, down, constant. Okay. So it says to state the open intervals on which f is increasing. So remember, we're looking from left to right, and we're using x values. So the farthest left I go is, according to this arrow, means I'm going forever left. So that would be negative infinity, right? So this arrow means I'm going left, and it means I'm going down. And then I'm increasing until I get to this dot right here. I'm going to go to the x-axis, and I'm going to put that value, which is -1. So, because that's at -1. So when I look at this, okay, when I look at this, this is the separation, right, where it switches from increasing to decreasing. So I'm going to highlight that line right there. So we're doing intervals, right? We're doing intervals, so that means I'm looking on the x-axis. And so I'm going from negative infinity until I hit that highlighted line, which is -1. So then my answer, so state the open interval on which f is increasing, would be from negative infinity to -1. So from negative infinity to -1, right? Okay, so now for part B, state the open interval on which the function is decreasing, on which f is decreasing. So again, we're doing open intervals. That means we're going to be using parentheses, and we want to see where we're decreasing. So I'm going to go ahead and look at that little section there too. So where did I stop decreasing? Was at this dot right here. So I'm going to go ahead and just kind of highlight that line right there. And so I stopped decreasing at that point here, so I'm highlighting the line where I stopped decreasing, and I'm looking to see where that is at. So that is at +1 on the x-axis, so it's at +1. So I'm decreasing, so this dotted line is where I'm decreasing, in between the two highlighted lines, which are at -1 and +1. So from -1 to +1. For part C, state the open interval on which the function is constant, on which f is constant. So constant is this section here, right, where we're horizontal. And so it doesn't stop going constant past this highlighted line, right? So at this highlighted line, and then the arrow is forever to the right. So I'm starting at the highlighted line, which is at 1. So we're going from left to right. And then it's forever to the right, so positive infinity. Okay, so from +1 to positive infinity. Okay? And then now the next part is state the domain and range. So domain and range, we want to go ahead and finish filling out the 4 corners. Let's go ahead and do that. So I already had filled in this arrow. So this arrow is going down and left. So those were both negative infinity. And then I have one more arrow. I have this one, so pointed to the right forever. So that would be positive infinity. And then there's no arrow pointed up or upward, so I want to find the highest space on the graph, so that's right here, and count up from the x. So that would be at positive 3. Okay, so domain is left comma right. So domain so left comma right, infinities get parentheses. And then for my range, let's scoot this up just a little bit, is bottom comma top. So bottom comma top, so negative infinity, comma 3. And it will be a bracket because it doesn't say anything about open, right? No open. So this is a closed dot, so then this will be a bracket on the 3. Okay, and then now for part E, it says state the coordinates of any relative minimum of f. And then I just saw this note over here, so this should be scooted over to here. So let's move that. So this should say relative maximums on this side. Just a little typo there, or editing. So let me scribble this out, okay? So state the coordinates of any relative minimums of f. So we're looking for relative minimums. So minimums, remember, is when we go from decreasing to increasing, and it could either be absolute value, quadratic looking. So there's no place where it switches, right? The only place I see it goes from decreasing to constant. So decreasing to constant. So that is not a relative minimum. So then we would just write none. Right? No place where it goes from decreasing to increasing. It goes decreasing to constant. So now for part F, state the coordinates of any relative maximums of f. So any relative maximums of f. And so a relative maximum definition is when we switch from increasing to decreasing. So here's a portion where it goes increasing to decreasing. So that means that dot right there is a relative maximum. That dot is a relative maximum. So that was at -1 on the x, and then 1, 2, 3 up. So it's at -1, 3. So now remember, this is an ordered pair. So that's an x value and a y value. So this can be kind of confusing. So you always need to know in context what you're answering. So for example, part B, where we have this -1, 1, that looks exactly like an ordered pair. However, it says open interval. So these are both values of x, from -1 on the x to +1 on the x. This is asking for a coordinate, so this is an x value, this is a y value. So we are at -1 on the x and 1, 2, 3 on the y, okay? All right, so far so good. Okay, so now for the last part, we have to write a piecewise defined function that accurately represents the graph of the function shown above. So what they are asking us to do is write out the equations for the functions I have up here. So they're telling you that there's two graphs put together. And if I look, I have the graph of a quadratic and I have a graph of a constant. So I need to write the equation of the parabola. So I'm going to start with that. So the equation of the parabola. So I'm going to do that over here onto the side. So for the parabola, I need to know my formula. So just as a reminder from last unit, that's the equation for a parabola. And in order to do that, I need to know what are the values for h and k and x and y. So h and k and x and y. So the h and k is my vertex, so that's that dot right here. So that was at -1, 3, so that's h and k. So -1, 1, 2, 3, so there's hk, and then I just need another dot to call xy. So I'm going to use this point right here since it's marked pretty close. So that dot is at 0, 2, so 0, 2, and that will be my x and my y. So I have two ordered pairs, and so I have my x and my y, my h and my k. So I know this is kind of low in the back. So I'm going to write them down here so we have them. Okay, so we have the hk, okay, so I'm just transferring it so I can scoot it up high. So normally I would not write this down, right? I would just look at my graph. So replace the y with the y value, so that would be 2, so I'm going to go down to here. So y with y minus my k, replace x with x, and then h with -1. So a double negative is a positive. 2 minus 3 is -1. 0 plus 1 is 1, and then when I square it, it will stay 1. And then divide both sides by 1. And then now replace the numbers up here. So remember that your a value replaces, and so does your hk. So you're going to replace those 3 numbers there, but you don't replace your x and your y. So you want x to stay x and y to stay y. So I have y minus k, and I'm looking up here for the h and the k again, a, which I just solved for, and then x minus h, and again it's minus a -1, so that'll turn positive. And then there's that equation, okay? So that's my parabola equation. And then now for the constant, so to do the constant, I'm going to drop this down just a little bit. So this is a special case, so I look to see it's going horizontal. So that means it would cross the y-axis, and where does it cross the y? It crosses at -1. No, at -2. So it crosses the y-axis, so I'm going to extend this just a little bit so I can see that better. So that's at 1, 2. So for the other equation, it would just be y equals -2, because it would cross the y-axis if it extended forever, and it crossed at -2. Okay? All right, so those are my 2 equations. So I have my quadratic, right, which is the y minus 3, and then I have my special case y equals -2. So now that I have that, I have to write it into piecewise notation. So that's a little different. So we haven't done this part before, so I'm going to cloud these though, so I have them kind of handy dandy. Okay, so here is the equation. So I'm going to write f of x equals, and so this is going to be using the top and bottom, right? So we have a top and a bottom. So I'm going to use the curly bracket. So we're going to try to draw that as best as we can, which I know it's hard to do. So think of it as you're drawing a forwards S and then a backwards S. So a forwards S, backwards S. Okay, so my top equation is right here. So we know that normally this -3 would be on the other side, and we have to move it like back and forth. So I need the y to be by itself to go into this notation. So that means I'm going to add the 3 over to the other side. So I still have -1 x plus 1 squared, and then I'm adding the 3 over. And then on this one here, I have y equals -2, so then just a -2. So all I'm doing is writing what's on the right side of my equation, because here's the equal sign, right? So equals -2, and then equals all of this, but I want to move that 3 over, okay? So that's the equation of the quadratic, equation of the constant. Okay, so I know this is a lot, but we're still not done. Okay, we're still not finished. So the other thing we need to do is we need to say, well, where are these values? Like, where am I graphing? Where is this at? So I'm going to go back to my graph, and when I look at this, I see that I have the separation is at this highlighted line, right? This last highlighted line is where the 2 graphs separate from each other. So here's the parabola, quadratic, and here's the constant. So they're separating themselves at x equals 1, right? They're separating themselves at x equals 1. So when I go to the left is the quadratic, when I go to the right is the constant, okay? So at 1 is where they're separating, so I'm going to do a little semicolon here. So when x is less than or equal to 1, because that's where they split, And for this one here, I want to say just greater than 1. I don't want to put equals on both. Okay, I don't want to put equals on both. Okay, I could because it is a common dot, but that's not what we do normally. Okay, so if you had put the underline here and not here, that would be okay as well. So where did they separated? They separated at 1. So you have x is less than or equal to 1 and x is greater than 1. Okay? All right, so now what I want you guys to do is I want you to try example 2, okay? And I want you to work with your partner, see what you guys can do, and then I will project later what the actual answer is, okay? So that is what I want you guys to try. Do your best on this and see what you can do. And we'll look at the answers in a few minutes, okay?